Okay, maybe it's time, so let me start. Yeah. So good afternoon, everyone, and good morning to some of you, and good evening to some of you too. I'm Xiao from France, and I'm very happy to introduce Professor Xiaoping Qian, the keynote speaker for the SPM conference. Xiaoping Qian is the Elmar and Janet Heiser Professor in Mechanical Engineering at the University of Wisconsin-Madison. And before joining the University of Wisconsin, he was at the Illinois Institute of Technology. He obtained his BS and MS from Hwa-Song University of Science and Technology, and his PhD from the University of Michigan. His research focuses on computational design of multi-physics systems, topology optimization, shape optimization, and design for additive manufacturing. He's an elected fellow of the American Society of Mechanical Engineers, ASME, and has served as an associate editor for several international journals, such as Journal of Computer-Aided Design, ASME Journal of Mechanical Design, Journal of Computing and Information Science and Engineering, and Journal of Manufacturing Science and Engineering. So today he will talk about his work on topology optimization for additive manufacturing. So please, Xiaoping.
Okay, thanks, Hawan, for the introduction. I want to thank the organizer for inviting me. So here, I just want to share with you how to account for additive manufacturability constraints during topology optimization. So what is topology optimization? Topology optimization is a design method. For example, you have design domain, you prescribe the boundary condition, loading, then the structure is automatically emerge as a result of a design method or design algorithm. For example, here, the blue color represents void, the orange color represents solid, so distribute solid. So the distribution material is automatically determined from the topology optimization algorithm. So that's the idea of topology optimization. Here I show you an animation. Start with initially green color, gradually evolves into blue and orange. That is void and solid. You start with intermediate density. Here density is a representation, a pseudo density to represent the different type of material from intermediate density to void and solid. This density-based topology optimization is perhaps the most widely used method. And for example, this can be used for the heat conduction. You can see very intricate details has emerged as a process of topology optimization. You can use it for thermal fluid problem where we solve Navier-Stokes equations. So here you can see very complex geometric features emerged. And these are the component design you could also use in a Uli segment of paper where they used a gut voxel to design aircraft wing structures. So you can see a very complex structure can be used. So by now, topology optimization is a quite mature method. So we're looking at density-based method. There are other methods like level set, phase field of topological derivatives. As you can see, complex geometry or topology could emerge out of this software or tool. So how do we fabricate it? So that along comes with additive manufacturing. So you can see here, a very, very nice part has been built. Additive manufacturing is capable of building parts of very complex shape without part-specific fixturing or tooling. The reason it could do so is because it introduced something we call sacrificial support structure. So support structures here only to support the part building process. It itself is a waste of material, waste of build time. If it's possible, we would like to get rid of it. And also, in some manufacturing processes, such as metal additive manufacturing, how do you get rid of this support structure could be a challenge. In metal parts, to get rid of support here, you would have to use a wired EDM. So that has these accessibility issues and special tooling issues for this removing metal support structures. So the question arises, is it possible to design these parts so that they can be printed without support structure. So we want to answer the question, can we do topological optimization during the design stage so that the resulting design can be printed automatically? So that's what we want to address. The other type of problem we thought this could be relevant is in the case of support structure. As you can see, people are already looking at perhaps we need some porosity in the support structure. Depending on load, we have lighter materials, so we have higher porosity. Then we want to ask, can we design in a more principled method based on a mechanistically way design or use topology optimization to design support structure? Here you can see this is utilize the idea of a tree to support this one. And then can we also using a mechanics-based design to come up with the support structure? Keep in mind, these trees are designed in a way so that it meets particular overhang angle, so the part can self-support. So the idea is you want a support to self-support. So you don't want a support structure for support structure. So this is a problem we want to address. We want to account for additive manufacturability during topology optimization. So how can we account for this support constraint during topology optimization? That is what we want to address. Now, let's take a look at the technical issue we're addressing here. This is a very common beam. If you're looking at this structure, you can see where do you need support structure. If you're looking at this boundary C, perhaps you don't need support because you're facing up. If you're looking at boundary B, you're facing down, you do need support. Looking at boundary A, you may or may not, because here it depends on overhang angle of the part and also depends on the process capability. You may or may not need support here. And so if I have the imposed looking support structure, this is a shaded area, that's where I need support structures. If I look at this side, even though it's facing down, but the slope is a little bit higher, so it does not need support structure. So the challenge, of course, is you can see to determine where you need support, you really need to know the boundary slope. But in density-based TO, there's no explicit definition of boundary because each element or each node, the density evolves independently and the boundary is evolving. So how do you relate this support to a point-wise density in a differentiable manner is an interesting challenge. And there are other methods, for example, based on filtering, where they are not necessarily using a gradient-based approach. We're interested in using gradient-based approach into topology optimization. The reason is topology optimization, as we explained to you earlier, commonly involves multi-million elements or nodes, sometimes even billion element nodes. So a very large number of optimization variables. So traditional evolution methods will be inefficient. So we would prefer a gradient-based approach. So how do we relate this support structure to the density in a differentiable manner is a non-trivial issue. If this is not challenging, let's look at another aspect of it. Because this support structure apparently depends on the build orientation. So if I change this domain a little bit, rotated, build orientation is still vertical. So you can see this area no longer needs support because this part can self-support now. And if I rotate this part the other way, so you can see only this part needs support, these do not need support. If I rotate this domain slightly a little bit more, like here, you can see even in this area, we do not need support. So slight rotation leads this one to this one, so we don't need support. So you can see the support volume is actually not differentiable with respect to orientation. So how can we do that during topology optimization? I think that is an open challenge. So right now, there are a lot of active research trying to tackle this issue, but people try to assume a build direction and then do topology optimization, or you sample build orientation. So here, we want to present all these issues with one formulation that is differentiable with respect to both orientation and density. So this is what I want to talk about today. So we want to talk about how we can control the undercut during topology optimization. How can we control the overhang angle so the part can self-support? And how do we control topology as well as a build orientation in optimization process? we will introduce one formulation that can tackle all three problems. And then we will show you an artifact of our formulation and then how we can use the second derivative-based measure to overcome this artifact. So that's what we're going to talk about today. So what we're going to talk about is actually can be represented through one concept we call the projected undercut parameter. So if this is a design domain, assuming build direction B, if you look at here, only this shaded area is actually needs support. Oh, this is an undercut. The amount of undercut I'm going to characterize by the horizontal length we call project undercut parameter. If it's 3D, that will be horizontal area. So you can see if this P becomes small, the amount of support becomes small. When P becomes 0, and then there's no support needed. So how do we compute that? So we know this density is 1, this area is 0. So density gradient, this gamma represents density, points this direction. Its dot product with build direction from cosine alpha. This alpha becomes overhang angle. As you can see, this alpha is overhang angle. So this directional derivative of density or density gradient with B build directions dot product gives overhang angle. So we compute this PUP, project undercut parameter P, by a volume integral. So this quantity can be computed pointwise. And then this gives you overhang angle. So we suppress that facing upward where you do not need support. Then we do a volume integral. That's the idea PUP. So with this idea, we can compute the support structure bypassing the need for explicit boundary. And we utilize the fact in optimization for converged design, density gradient only exists in boundary. It vanishes interior to exterior. And this formulation is differentiable with respect to both build orientation B and density gamma. So here, let me show you this example we showed you earlier. For this part, if I'm looking at the directional derivative here, you can see this B facing downward. So it's density from 0 to large, density gradient goes up, and the build direction up, so the directional derivative is positive. On the other hand, here is negative. On the side is negative, and here is positive. So here you can see only positive area you potentially need support. So I'm going to be using heavy side to suppress those things. So that's the positive that could potentially need support. If I do an integral of this one, that gives you the measure of P, the horizontal length. So here is the design, the horizontal length of 2. You see the measure of horizontal length is, the sum is 2. The design domain is 6. So we have a geometric measure, this P, characterize the horizontal length or area you need support. And you can, again, this is directional derivative with heaviside suppression. So here you just do a volume integral, and this thing is differentiable with respect to density. And if you have grayscale design, you would have similar measure here. Density gradient only appear on a boundary. So that's what you have. And then we apply this formulation into topology optimization. This is like classic optimization formulation, density-based. We're looking for displacement and distribution of materials. Here we solve a minimum compliance problem and equilibrium equations and volume fraction constraint. The gamma is density. Here the PUP constraint, that is a horizontal length or area you need support. It should be smaller than a threshold. And this is grayness constraint. So when gamma equals 0 or 1, this is becomes 0. Otherwise, we penalize intermediate density. And then here we can see how this one looks. In a 2D design, you can see this is allowed PUP constraint. Initially P 3.5, 3, 2.5, and 2, very small number, 0.1. So you can see that the support structure, allows support structure becomes smaller and smaller. So we can see indeed this PUP controls the amount of undercut. And you can also notice as we tighten this P, the cost function goes up. So in 2D, when you tighten the constraint, the design, so the cost function is worse off, so the compliance here. And same idea can be applied in 3-dimensional. So here again, 3D beam structures. If I do not impose any undercut constraint, the horizontal area is about 3.6. And you can see this area needs support. These are different view of same structures. So if I impose the horizontal area to 2.1 to a 2.0, 1.0, 0.5 to small 0, here you can see the allowed horizontal area becomes smaller, the actual constraint is satisfied. And you can see here the amount of PUP or the area needs support becomes smaller and smaller and smaller. So we can see the P0 controls the amount of undercut. And here it's interesting is that when we tighten this P0, the cost function is not necessarily worse off than without this constraint. And until this P becomes really tight, so you can see this one is actually worse than here, and this one is far worse than this one. So we can have a trade-off between the tightening the undercut and the cost function. The reason this one not necessarily worse off when the smaller, when the P is very loose, we believe is because there could be many local minimum in the 3D design. The 3D design space is much larger. So we can see this P formulation or PUP formulation really allow us to control the amount of undercut. Now we would like to extend this formulation to overhang angle. So the idea is still the same. Instead of just to heavy-side thresholding downwards boundary, we're only thresholding its boundary slope that is smaller than alpha 0. So here we're looking at thresholding not a direction derivative, rather normalize the direction derivative, because this one corresponds to overhang angle. So only overhang angle is smaller than alpha 0, so they measure this part. When this part smaller than threshold, then basically everywhere else is like this one. So the part can be printed without self-support. So that's the only difference between undercut-based formulation versus overhang angle-based formulation is where we do heavy-side thresholding here. With that, this is our formulation. Again, the same previous formulation, standard formulation, compliance cost function, equilibrium equation, volume constraint, where we just here is PUP constraint. We replace this heavy-side from positive and negative to a particular overhang angle. And then here's the example. So this is 30-degree overhang angle, and this is optimized design. You can see if I take a directional derivative, that's where you can see here. And downward is positive, upward is negative. If I take this is normalized direction derivative, that's what we have, heavy side here. We do a dot product, that's where the constraint is violated. As you can see, this is very small. You see, if you tighten it, that can effectively control the overhang angle. And this is animation. You can see initial intermediate density green. As the optimization evolves, it becomes blue, that is void, or orange, that is solid. And you can also see this design boundary meets this 30-degree overhang angle. And here is an example of different overhang angle. Here without overhang constraint, that's the design you see. You can see you have downward facing design. So this would need support structures. Now if I can impose 15 degrees, 30 degrees, 45, 60 to 75 degrees. And if you are looking at the minimum overhang angle of each design, you can see this is the evolution from A, B, C, D, E. So indeed, this P alpha controls the overhang angle of the design. And also the cost function goes up if you tighten this overhang angle. And then one thing we should be careful is sometimes you may notice that this type of design appears that everywhere the overhang angle is satisfied, but you may not be able to print this design without support structure on the side. To do this one, we just impose a sidebar constraint where we impose normal. Here we use boundary left side normal, right side normal. We use a heavy side function where any function facing basically this downward on this side, if we do a projection, that's what we have. If we control this one, and then you will see this is controlled, and this side will not be affected. And if we do this one, and this will be not affected. If I impose the scillating zone constraint, that's what you have. So here is what you have, and here is the resulting design. So you can see different different optimal design could emerge if you impose the scillating zone constraint. The design will self-support without much penalty to the cost function. And then when this idea is readily extendable to three-dimensional, here's a part. This is part can self-support, and you can looking at the animations here. And this is printed in the FDM machine where this commercial software using Dimension Elite, it automatically needs this black color support structure. If we're using printed part on the DaVinci 2.0 with open source FDM machine, you can see this part is printed on the machine. It can be printed without the part. For this part, it leads to substantial amount of saving of support structure. So we don't need this amount of material. And then now we have an approach to control the part. So the part can self-support. We start, where can we apply this feature? Well, the obvious place is to use this part to design support structure. So the idea is you do not want to support for support structures. So here's what we want. Here we have a beam structure, this gray is beam structure. This red color is the design structure. This is like tree-like structure is topology optimized support structure. Our formulation is the following. We want to minimize the support materials under this distributed load from the beam boundary. And we want the beam to self-support. There's an overhang angle here. And this is design. So this is pretty much like many of the bridge we see here. And this is a topology optimized design here. We can extend the same idea to three-dimension. Here's the three-dimensional beam structure. Here's cut off this top bridge, and this is the design look like. And this is actually a printing process. So this is a printed part. And this one leads to 43% of saving of support material over commercial software use of support structure. And this is work is done by Francesco and Vlad here in my group. And then we being at Wisconsin, so we want to support the Wisconsin Badger. So here is actually Wisconsin Badger. And this is the 3D printed support structure that is topology optimized. Here is the part. Here's topology optimized part in the model. And here you can see a printing process. So you can see both the part and the support structure can be printed directly without any additional processing. And this support structure was optimized with 400 million elements, 1.2 billion DOFs, involving 300 processors from our campus here. Now I can show you a few more examples. Here we want to design support structure for a dome. And this is top, like a hemisphere dome. And this is design support structure. Depending on the height of dome, we get different structures here. And all these structures are self-supporting. One thing we have noticed is that although we have this PUP constraints to design support structure so that they can self-support, in practice, we found our formulation, when we impose this mechanical load under minimum compliance, under elasticity problem to minimize volume, it turns out the support structure can self-support. Our overhang constraint is rarely active. And here's the actual printed part in FDM machine, in SLA part, and here's a model, and here's a printed part. All these things can self-support. Now we got this one, we get the capability of controlling slope for control support. We can also use this one to control the surface roughness. So the idea is the following. If this is for heat conduction problem, if I control the overhang of 30 degree, 45 degree, 60 degrees, so this part can be printed without support structure, depending on the process capability of your machine, whether you need support or not. Now, sometimes you want it the other way. Instead of all the part facing up, you want the part slope facing down. the reason or the assumption is the following. When you have part surface facing downward, typically the surface roughness is bad. So you have a very coarse surface. It could actually be advantages, be taken advantage. That is, when the rough surface, sometimes you can transfer better heat. So you can promote heat transfer. So that can be beneficial in the heat thermal management application. So if you want to downward facing surfaces for heat conduction, so this sort of design you would have. And here we can, same formulation, all we need is by controlling this boundary slope. Now, this upward, this is downward, now you can control both. So both upward and downward slope. So we can essentially have different way of controlling boundary slope in order to enable support control or surface roughness control. Now we have explained how this PUP formulation enables undercut control as well as overhang control. Now let's look at how it can be used for orientation optimization. So here, suppose we have a two-dimensional structure. This is design domain. Here is fixed. We have a load. It's a hook. And if I do not have any orientation control, this is optimized structure. So you can see for this kind of design, there's no particular orientation you can choose that can be printed without support structure. So we want to find a support structure that can be printed without support structure. And here's what we found out. And here is the B star is the optimal build orientation. Here with 45-degree overhang angle. And this is the part. If I build along this direction, this part can be built without any support structure. So here we're using B as a build orientation. It's parameterized by angle theta with respect to horizontal axis. And with respect to B, build direction, you can define a horizontal plate. And then you have this overhang angle is alpha. So that's our notation here. And then actually our PUP formulation defined here, basically undercut smaller than overhang, smaller than alpha, this is length, this P. If you rotate, you can also define this projected length. Right? This basically that's a definition. In the previously we assume a fixed B, and now we make this B as a variable. So this is differentiable with respect to B. In addition, we also define a external support. This is area that needs support based on density here. We define this boundary Q. So this controls the support outside of this design domain. And if I'm looking at this orientation change, you can see this part ABC boundary. If I change this build orientation B, then this directional derivative change here. For example, here become a little bit lighter, and here almost vanish, and here become vanish. And if you're using heavy side, this one does not, this part disappear. So that is to say, this slope does not need support at all if you build along this direction. On the other hand, this slope needs support in this direction. As you can see, point-wise directional derivative is differentiable with respect to this build orientation. So then we have the following optimization formulation. We are looking for density distribution and build orientation phi and psi in 3D. This build direction, we can represent build orientation B with two angles, this phi and psi here. And then this is equilibrium equation, volume constraint, and then this is control the overhang, the overhang angle length that needs support, and this is external support we control it. And that's our formulation. And then let's look at the beam here. If I don't impose any overhang angle, that's the design we have. And now, if I impose 45 degrees, assume this is fixed vertical build direction, that's a default one, and that's the design we have. And this is a cost function. As you can see, if I impose overhang of 45 degrees, the cost function actually becomes larger, which is worse off design. But this design meets the overhang angle. Now, if I change orientation, making this orientation this direction, and then this 45 degree, this design can be printed. So this is actually much better than this one and than this one. So right now, how do we find an optimal orientation is the issue. Now with our approach, we can do gradient-based optimization. We found optimized build direction also along this design. So it's nearly identical to this design. So you can see this optimized design and no constraint design is nearly identical. So this, you can see this orientation optimization is capable of finding the best orientation here for this particular example. And then here we show you the density evolution, orientation change, and the PUP integrand during the optimization process. So here to show the build orientation change, we actually show the design domain change by assuming fixed build orientation. This is for visualization purpose. If I assume B along this direction, so you can see design domain change from here to here to here. With 45 degrees overhang angle, this red color, you can see you have some violation here. And then the converged design just meets the overhang angle constraint. This is density evolution. The rotation of design domain represents the orientation change. This is a PUP integrand. Initially, you have a lot of violation, and then toward the end, you only have this small violation along the boundary. That's the constraint by the PUP constraint. That's the constraint active. And if you're looking at this 2D design, this two-dimensional hook, and this is what if I impose 45-degree overhang angle for assumed vertical build direction, that's the design we have. And you can see the design is worse off than this one. If I'm using build orientation optimization, this is the design we have. You can see this one is actually better than assumed build orientation, even though slightly worse off than no overhang angle constraint. And here is a evolution process. You can see the design domain orientation is changing, the density is changing simultaneously, as well as the overhang angle. Here you can looking at the convergence history, the compliance coming down, basically the optimization is converging, the build orientation theta is converging, and the volume constraint is active here. Then we can extend the same formulation to 3D, because we want to emphasize 3D is because our formulation is same for 2D and 3D, and because it's gradient-based approach, it is computation efficient, so it can be readily extended for 3D. Here, if this is fixed, we put the load here, and this is optimized design without support structure. And you can see it needs a lot of support here, and also a lot of support outside design domain. And here's build orientation change. You can see very little external support, and there's no support internally, and this is optimized orientation. And this is the cost function, does increase the cost function here. And then here's 3D beam. You can see this one, optimized 3D beam. It needs support structures. And there's actually, in fact, a lot of support structure. If you don't impose any overhang angle, it needs a lot of support structures. And then using overhang angle alpha equal to 45 degrees, so the part can self-support without support structure. And we'll also find optimized orientation. And this is optimized orientation. You can see along this direction, the part can be built without any support structure. Here's another view of this one. And here is three-dimensional rotated view. You can see along this particular orientation, this part can be printed without support structure. And here is a visualization of the optimization process. We're visualizing orientation on the Gaussian sphere. Each point on this Gaussian sphere represents the orientation. And here is design domain. You see density evolution. You see orientation evolution here. Different color represents a cost function here. And here is the attribute part. You can see this part, you need external support, but inside the design domain, you do not need any support structure here. Here you have cost functions, red color, and this green and blue are the two angles. You see convergent angle, and then this cyan color is the volume constraint. All these constraints, this constraint is active. And this, if I fix this orientation, optimize build orientation, rotation in this way, design domain becomes this here. If I take cross and cut it, you can see this part boundary along this red line. This red line 45-degree overhang with respect to this optimized build direction. So you can see this boundary is along 45 degree, that is constraint, overhang angle constraint is active. So this part can be printed without any support inside this design domain, but it does require a lot of support structure outside the design domain. If we impose our earlier formulation Q, which is external support, and then you can see this is part. So it does not need any external support. So this is 3 design. No overhang angle constraint. Here is only support constraint inside design domain. Here's both inside and outside domain. These are 3 different designs. And you can see the cost function is actually, for 3 designs, this is the cost function. And this is work done by Chunfu, which is published in the journal Additive Manufacturing. So now I have shown to you how our PUP formulation is differentiable with respect to density or orientation. It can be used to control undercut, overhang angle, as well as optimize build orientation. Now, I just want to quickly go over with you that it does have an artifact of our formulation. That is, if we impose overhang angle, you can see this is perhaps 45-degree overhang angle. You can see everywhere is volume constraint, angle constraint is satisfied, except these 3 points where you have downward facing point, part cannot be printed here. Even though you do integral formulation, the constraint is fine, but you have this oscillation. So in our initial formulation, to overcome this issue, we increase filter size. So for example, from 15, you have this issue here, include 20, this oscillation sort of suppressed, it's still a little bit, including 25, you don't have oscillation. So by the way, our formulation is also applicable to level set. As you compare, in fact, this has been applied in the context of level set. This oscillation issue also appears in level set based implementation. It has been noted by Allaire as in dripping effect. So how do we overcome this sort of boundary oscillation when we do this overhang angle based constraint formulation or density gradient based formulation? So we recently take a look at this issue, and this is work done by Francesco here. And here it's a design without overhang, that's what we have. If with overhang, you can see this point-wise you have that constraint violation, make this oscillation, make this part not printable. So how do we overcome this? This is the problem we want to resolve it. So here, if we observe this oscillation, this is a problem. How do we get rid of this one? And so here's the idea we use. We want to characterize this oscillating boundary. In order for a boundary to oscillate, there had to be a tip. Of course, if you have a tip, you also have a valley. This valley perhaps somewhat similar to this top, this horizontal hole here. Now, how do we characterize these things? If we're looking at the draw horizontal line, if you look at density variation across the horizontal line, we will see the difference between the tip and the valley lies in secondary derivative. For the tip, the density variation is necessary from 0 to 1 to 0. And for valley, the density variation is necessary from 1 to 0 to 1. So that is secondary derivative from 1 is smaller than 0, 1 is larger than 0. Of course, if you have a top of a hole, this is also larger than 0. Or a short horizontal overhang, you would also have that. So what our assumption is, if you have boundary oscillation, you must have a tip. So if we could just penalize the tip, then we essentially get rid of the valley. So that's we call second derivative based measure to remove oscillation. And here's our oscillation measure, the second derivative. And here these second derivative extract tip, and this first derivative extract the boundary. And then together, you can see we can separate this valley from the tip. And this is a measure, positive and negative here. And more specifically, if you're looking at first derivative, that's this one. Second derivative, you can see positive and negative separate tip and the valley. And here you can see if I suppress the the positive line, basically all the valley has been suppressed. And if you're looking at first derivative heaviside, and then this extracts all this tip and the valley here based on the overhang angle. And if I do multiplication, then essentially I only I can extract the tips. So that allows us to penalize it. And here the formulation, there are perhaps multiple ways to penalize this oscillation. We use two strategies. One is filtering, that is, we only penalize this density when there's oscillation. So this density is large only when the oscillation is large. Or we penalize cost function. So this is integral of the oscillation, where this P we call P norm, so that this is differentiable. And then again, this is designed so that it can be used in a gradient-based formulation. So let's looking at filtering. Here we actually looking at anisotropic filtering. So the idea is, in our earlier formulation, if we use isotropic filtering, for example, 5, filtering here 5 to 20, and then this oscillation has been suppressed, but this design becomes a little bit gray. Now, if we're only using large filter radius along X direction, we also have the effect of what? Suppressing the oscillation. But Z is small, so this actually makes the design a bit sharper. And so keep the design less gray, and also increasing Z does not contribute to suppressing the boundary. So as you can see here. So that's why we use isotropic filtering and adaptive filtering. So this is our formulation. So if the oscillation is large, we just increase this filter radius in downward phase. This is directional derivative facing downward phase. If the oscillation is small, we just reduce the filter radius so that allow whole new creation, allow topology evolution here. So one is for controlling increased radius, one is controlling reducing radius. And then here's the design, 30 degree, 45, 60. This is with anisotropic filtering. Here is with cost penalization. You can see these are different designs. And if you compare without second derivative, this is cost function, you can see this delta C with respect to the formulation without second derivative. Typically, this leads to increase the design is better here. And you can see, especially at high overhang angle, design is substantially better with this formulation. And here you can see with this adaptive filtering, if you have overhang angle with large adaptive filter rate, this is the design. For 3D design without overhang angle, you can see this one is support structure. Here, this imposed overhang angle, you need this 3-dimensional oscillation. With adaptive overhang angle, this part can be designed without support structure. Can be printed without support structure. And here is adaptive filtering. You can see here using non-adaptive filtering, smaller filter, you have oscillation, and large filter, that's what you have. It's still perhaps here you have a part that cannot be printed, and here increase to 25, and that's a part can self-print. If we're using isotropic filtering here, and you can see global 25 in all directions, this cost function is much worse than this one. This is the design you would have. And here you can see design evolution from iteration 50 to 300. You can see you still have oscillation earlier. The topology evolves, so this part can be printed. And here iteration 150, you can look at the distribution of filter rates. So you can see in this case, the filtering is both temporally and spatially adaptive here. The color represents the filter radius. The highest color is 25, as smallest the filter radius is 2. Filter radius varies from 25 to 2. And we can also apply our formulation with cost penalization. So basically, if you have oscillation, you increase the penalty here. And if we don't, without penalization, this is design. With penalization, this is design. So you can see this free from oscillation. The net effect is you don't have this part, and so this part can be printed without problem, and it essentially creates a pillar in this area. In 3D design, similarly, you have oscillation here. If you impose this penalty weight, and this is the design you have. And in summary, here we have presented you a formulation that we call projected undercut pyramid. It has specific geometrical meaning, which is horizontal area that needs support. It is numerically, it is volume integral of heavy-sided density gradient. It is one constraint, so it can be easily incorporated into optimization formulation. It is easy to compute, so it can be implemented both 2D and 3D. It's just differentiable with respect to density, so it can be used in density-based, gradient-based topology optimization. It is differentiable with respect to orientation, so it enables simultaneous orientation and topology optimization. It can be applied in level set-based formulation as well, even though we implement in density formulation. We demonstrate this measure in the case of undercut control, overhang angle control, as well as build orientation optimizations. If you're interested in more details of this work, you can see these are publications initially appeared in 2017. And then this, I want to thank our student and the collaborator, Francesco Verlat, for this support structure design, and the train for overhang, for orientation optimization, as well as Francesco for second derivative based measure. And that's all I have. And I want to thank you for your attention.
Thank you.
If you have any,
thank you. Yeah, any questions from the audience? I see there's something in the chatting window. Yes, it's from Charlie. Is the additive filtering method can also be used to remove the fragile regions with small feature size from the result of TO? Do you see the question?
Can you, let's see,
You click on the participants icon.
I see.
Then normally this chatting window is at the bottom of this participants window.
Okay, so maybe, do I need to stop sharing screen in order to?
Not really, but I can read the question for you if you
want.
want.
Please.
Yes, yes. So question from Charlie, is the additive filtering method can the additive filtering method also be used to remove the fragile regions with a small feature size from the result of TO? Topology optimization.
Small feature size, is this question about feature size control?
I guess it's about the application of additive filtering method.
Hi, Xiaoping. I think okay, let me ask you.
Sure.
I think the question is like, I see like you using the second derivative to evaluate and trying to detect some of the region where you need to penalize. So I'm thinking about what is possible to really using the similar measurement to penalize those fragile regions with small features.
I think it is possible, especially if those small feature, usually you have second derivative, you just penalize it. But here we assume a second derivative along a particular orientation. This one can be extended.
All right.
That's a very good idea. We haven't thought about apply to different manufacturing process. But you can see our formulation is basically if you have oscillation or valley, and then if we can capture those oscillations using second derivative, then this formulation can be useful.
Right. Thank you.
Okay, I have one question, Xiaoping.
Sure.
What about another alternative? I'm not really in the domain, but I was thinking that if we can approach the problem as the decomposition of the design object into components and printing parts by parts, one part after another, and then we glue them together to obtain the final model. Then I think the problem becomes quite different from the other way around. So I want to know your opinion about this.
I think the idea of decomposition, that's a very good idea, so that you can be printed each part individually without support structure.
Yeah.
That is possible, and that's also a very good idea. But that may have limitation in terms of how do you combine parts together. And also you're assuming you have a CAD model of part, and then you decompose it. Here, we're trying to say we don't even have a part model. We're trying to design a part so that the resulting design can automatically meet this part manufacturability constraints. So that's the idea. So your suggestion would work if we have the part already. So here we're trying to say we don't even have a part. So the topology emerges during the optimization. So in the optimization, both topology, both part boundary and the orientation are changing simultaneously.
Yeah, I was more thinking of like defining the parts. I mean, assuming that there's no constraint. I mean, it's us who define the parts in a way that there's no supportive structure needed.
I think that is certainly a good idea for designing a manufacturing process plan, so that part can be printed without support structure. But I assume decomposition requires you to have a part model, right? I'm not sure if I get your idea right.
Sure.
So.
Yeah. No. Yeah.
Maybe we can chat after offline.
No, I think depends on the object we want to print. So we have another question from the audience. Do you see the chatting window now?
For some reason, maybe because the way I use Zoom, I just do I need to remote control or stop sharing? If I stop sharing, maybe I can see it. Now I can see it. Okay, so the question is, the oscillation seem to some inherent problem formulations in the second derivative. I think this is first formulation we have seen, the geometric formulation. Okay, let me read the question. The question is that oscillation seem to be, there's potential inherent problem of the proposed approach. So the question is a second derivative penalization is the way forward, or should the future research be devoted to finding new ways